Hey everyone, welcome to my channel. So today we're going to be learning about sets and set theory. So if you're new to the concept or you just want to brush up on some skills or you're studying for an exam, sit back, relax, and I'm going to make it as easy as possible. Okay, so what is a set anyway? So a set is any kind of collection of objects. So it could be the set of your Instagram followers, or it could be your file directory on your computer, or it could be a shopping list. That's a set of things you want to buy. So today we're going to learn about how to write down sets, the notation for sets, and how we can speak mathematically about sets.
So let's look at an example. Let's say that anything inside this circle is part of our set, and we'll give our set a name. Let's call it set A. Okay, so this set contains this smiley face, it contains this angel face, and it contains this, let's call it a cool face. Now, what if we want to write down generalizations and observations about sets? Well, for that, we can use what's called the set roster notation. So the set roster notation is signaled by these curly brackets here. And then we write down the elements of the set separated by commas, like so. This particular set would be just the same as our set A here. It contains the same three members, the same three faces. Okay, let's look at a new set. Say we have a new set B, and it contains the numbers from 1 to 100. So 1, 2, 3. Well, you see that we are pretty quickly going to run out of space. So what do? One thing we can do is we can use these three dots called an ellipsis. And these three dots means that we skipped over a bunch of numbers. Here, let's say we skipped over 4 to 97. And we saved a lot of space by doing that. Ooh, let me do that again. Boom. Okay. Another thing we might want to say is, whether or not a particular object is an element of a set or not. So let's say, okay, is the smiley face an element of the set A? So to do that, we use what's called this pitchfork symbol, and it looks like this. So it looks like, the head of a pitchfork. That's why it's called the pitchfork symbol. And this is read that the smiley face is a member of the set A. We could also write something like 98 is not a member of the set A, and we also have a symbol for is not a member of. It's just the same pitchfork symbol, but this time it has a diagonal line through it. Okay, so let's look at some really important rules which are going to really help us understand sets. So here are three principles to remember about sets. Okay, so let's look at the first one. The first rule says order doesn't matter. Now, what does that mean? That means that anytime you have a set, let's call it A, B, C, it is exactly the same set as something like B, C, A. So the set containing the same elements, but just in a different order. We could have written C, A, B, and so on. You get the point. The idea is that the relative order of the elements within the set doesn't really matter when we're dealing with these kinds of sets signaled by the curly brackets. Okay, let's look at rule number 2. So rule number 2 is repeats don't matter. Now, what does that mean? That means that if you have a set like, A, B, C, A, this second instance of A doesn't add anything. It doesn't really contribute anything. We could actually just delete it. So no matter how many times you keep adding, an extra instance of A, you could add it 3 times, 4 times, 5 times, 60 times. It doesn't really matter. This set here just equals the set containing A, because these extra repeats don't count. They don't contribute anything. And then the last thing we want to talk about is that an element is not the same thing as the set containing the element. So say we have the set A, that is not the same thing as A. So for example, if we have the set A, and then it also contains the set containing A. How many members are in this set? Well, you might think it's only one because you might think that repeats don't count, but that's actually incorrect. This set actually has 2 members, 1, 2. So the reason it has 2 is because these 2 objects, A and the set containing A, they are 2 different things. So the set containing A is not the same thing as A.
Okay, so before we go any further, let's look at some examples and really get these concepts clear in our head.
So let's look at an example question. What is the relationship between the sets X, Y, and Z? Let's imagine that X, Y, and Z are different sets of the devices connected to our computer. So X is keyboard, microphone, mouse, and Y is microphone, mouse, keyboard. Now we know that order doesn't matter. So we can actually see that X has all the same elements as Y does. So the keyboard, the microphone, and the mouse. So even though Y has the elements in a different order, X is actually the same set as Y because order doesn't matter. Okay, let's look at Z. So we can see in Z that a couple of the devices are repeated. And we know from our rules that we've learned about that repeats don't count. So these additional instances of keyboard, we can just cross them out. They're not really contributing anything. We can also cross out the additional instances of mouse. They're not contributing anything either. So it turns out we just have the keyboard, the microphone, and the mouse. So it turns out all 3 of these sets are equivalent. Let's look at a couple more examples. Okay, example 2. True or false, is this set containing keyboard the same thing as keyboard? Well, we know that the set containing an object is not the same thing as the object. We know that A is not the same thing as the set containing A. So this one would be false. Okay, let's look at the next one. Let's use a different color. How many elements are in this set? So we've got 1, the cup, and then the second element is the set containing cup. Now again, we know that A is not the same thing as the set containing A, so the set containing cup is a new element. It's not a repeat, it's a different object. So we got 1, 2 elements, so the answer is 2. Okay, so let's look at a slightly more complicated example. So for any integer n, so an integer is a whole number, we'll talk about that in a bit, let S of n equal the set containing n and negative n. Okay, so let's look at a few examples and see if we can spot the pattern. So S of 1, so here 1 is serving as our n, so we need to copy this pattern here, but with 1. So S of 1 would equal the set containing 1. So the first element of our set has to be the positive number, and then the second one is the negation of the number, so the negative number multiplied by -1. So we would get -1. Okay, let's look at the next one. So our next one is S of -2. Okay, so the first element we put in is just n, which is -2. The second one would be the negative of -2, which would be +2. And the last one would be S of 0. Okay, so again, we put n in, so n is 0. And then we put -n. So there's actually no such thing as -0. So we would just put 0 in again. But okay, we know that repeats don't count, repeats don't add anything to an unordered set. So this would just be the same thing as just a set containing 0 on its own.
Now, sets can be absolutely anything you want, but there's a few sets which come up again and again and again, so it's really useful to get a handle on these, and all of these are sets of numbers. So let's have a look at these.
So the first really common set that we see again and again and again is the set Z. So it's the set of integers. So what's an integer? An integer is a whole number. This set would contain, well, it would contain 0. 0 is a whole number. 1, 2, 3, and it would go on forever towards positive infinity. It would also contain -1, -2, and it would go on forever in this direction too, towards negative infinity. So it would contain all the whole numbers. Okay, let's look at the next one. The next one is symbolized by the letter Q, and it's the set of rational numbers. Okay, so what's a rational number? A rational number can be expressed as A over B, where B is not 0, because you can't divide anything by 0, so we can't have A over 0. And then A and B are members of the set Z. So A and B are whole numbers, they're integers. So, you know, what would be some examples? We could have 45 over 100, we could have 6 over 10, we could have -2 over, 51, and so on. Now, one thing you'll notice is that all integers are also rational numbers. And let's try and see why this is. So 2 is an integer, but 2 is also a rational number because we can express it as 2 over 1, right? We are expressing it as A over B, where A, 2, and B, 1, they're both integers. So all integers are also rational numbers. Okay, let's look at the third set. The third set is symbolized by the letter R, and it means the set of real numbers. So real numbers are any number which occurs along the number line. So let's say we have a number line here, here's 0, we got 1, we got 2, we got -1, and so on. So let's see what's on the number line. We've got the integers, right? We've got -1, 1, 0, 2, and so on. So the integers are also real numbers. So if you're an integer, you're also a real number. Likewise, all the rational numbers are also real numbers. So rational numbers include the integers, but it also includes the numbers between the integers. For example, something like 3 over 2 would be somewhere on the number line. The set of real numbers also contains what's called irrational numbers. So these are numbers which cannot be expressed in this A over B format. So this would be things like pi, like √2, like √5. So all of these numbers appear somewhere on the number line, but they can't be expressed as rational numbers. So these would also be included in the real numbers. So the set of integers, we've got the whole numbers. The set of rational numbers, we've got numbers in the format A over B, where A and B are integers. And the set of real numbers, those are any numbers which appear somewhere on the number line.
Okay, so all of these guidelines so far have been ways to write down sets which only have a few members. But sometimes we want to write about sets which have a huge number of members, maybe infinitely many members. So let's get a handle on how to do that.
So far we've seen examples of this kind of format of notation, which is called the set roster notation. But sometimes we just have too many elements in this set to write them all down conveniently. So for this kind of situation, we might use what's called the set builder notation. So the set builder notation means that we have one big set, and then we form from that set a smaller set based on a condition. So we are building a new smaller set from a bigger set using a condition. So let's look at an example. Say I want to write down the set containing my Instagram followers. So here would be an example of that using the set builder notation. We are following this kind of pattern here. So we are taking items from a bigger set. So the bigger set here would be the set of all Instagram users, because my Instagram followers are from the bigger set of Instagram users. So we write the name of that bigger set on the left of this vertical line here. And then on the right of the vertical line, we write the condition which allows entry into our new set, right? So the condition on entry into our new set is that X follows my Instagram account. So the whole thing should be read that this is the set of X in Instagram users such that, so the vertical line means such that X follows my Instagram account. So here's the more general format. So we still have the curly brackets from the set roster notation. We have a variable, here the variable is X. We're saying X is from a bigger set. So in this example, it was the set of all Instagram users. We have the vertical line, which means such that. And then we have a condition on X's membership into our new set. Okay, so let's look at an example here. So Fatima wants to know the difference between these following set definitions. So X is in countries, X is in Europe, X is in country, France is in Europe, and France is in countries, France is in Europe. Okay, so I think the best approach here would be to try out a bunch of different values. So let's try out China. So that's a country, but it's not in Europe. Then let's try Hungary. So that's a country and it's in Europe. And let's try, I don't know, Meryl Streep. So that's not a country and she's not in Europe. Well, she might be in Europe, but she's not a country. Okay, and we want to see, do they fit in the sets A, B, or C? So let's look at set A first. So we need to replace the variable X with the value that we're testing. So, and see if the statement is true. So China is in Europe, that's false. So China won't be in A. Okay, let's look at Hungary. So again, we're replacing X with the item that we're testing. So Hungary is in countries, that's true. And Hungary is in Europe, so that's true. So Hungary will be in the set. And Meryl Streep is not in countries. So she's not from the original set that we're building from. So she's not going to be in the new set either. Okay, let's look at B. X is in countries, France is in Europe. Well, the same principle applies. We replace the variable X with the item that we're testing. So China is in countries, and then we test if the condition is true. So even though the condition doesn't contain the variable, which is a little strange and, creates ambiguities and confusion, it's still interpretable. So the condition is still true. France is in Europe. So China ends up being in the set B. So let's look at the second one. Hungary is in countries. And then we test the condition. Is the condition true? France is in Europe. Yes, that is true. So Hungary is there as well. Let's try Meryl Streep. Well, Meryl Streep, again, is not in our original set that we're building from. She's not a country. So she's not going to be in the new set either. Okay, let's look at C. So C, we've got France is in countries, France is in Europe. So C is just, we have a really strange name for a variable. We've called the variable, instead of calling it X, we've called it France. But if we've just replaced the name of the variable France with X, we just end up with exactly the same thing as A. The only difference is the change of the name in the variable, but apart from that, it's just exactly the same thing as A, so the answers will be the same as A. So no, yes, no. Let's look at a new example. What elements are in the following sets? Okay, let's just go one by one. So X is in R, so a reminder that R is the real numbers, and X is between 4 and 10. Okay, so it's going to be way too hard to list all the real numbers between 4 and 10. So let's write it on a number line instead. Okay, so let's say this is 4, 5, 6, 7, 8, 9, 10. 10. And it's going to be an interval between 4 and 10. Now we're going to use open circles to mark the boundaries of the interval. The open circles mean that 4 and 10 themselves are not included in the interval because x has to be strictly larger than 4, x cannot be 4, and x has to be strictly smaller than 10. So 4 and 10 aren't included, so we use the open circles to represent that. Okay, so that would be the interval of elements in this set A. Okay, let's look at the next one. So x is in the set integers, and it is between -4 and 2. So there won't be too many elements in this set, so we could just write them all down. So -4 won't be included because x has to be strictly larger than -4, but we'll have -3, we'll have -2, -1, 0, and 1. Again, 2 won't be included because x is strictly less than 2. Okay, so that would be our answer for B. Now, C is just the same as B. There's only one difference. The only difference is this a superscript positive sign. That means we're just restricting to the positive integers, so the integers where x is above 0. So it'll just be the same set as B, except only the positive integers. So we can see that in the set B, there's only one positive integer, namely 1. So this set will only have one member in it. It'll be the set containing 1.
Okay, now we know how to write down lots of different generalizations and observations about sets. So we know we can use special names for sets. So names like Z, Q, R for those special sets of numbers. We know about the set roster notation. So that's when you have the curly brackets and the little commas. And we know about the set builder notation. So that's when you have the vertical line and a condition on entry into the set. So now we've talked about that, here's a question for all of you.
Which of the following sets are equivalent? So we've got 4 sets here. We've got W, X, Y, Z. W is the set containing apple, banana, tomato, and orange. X is the set containing tomato, orange, banana, and apple. Y is the set containing tomato, banana, grapefruit, and kiwi. And Z is the set containing kiwi, tomato, grapefruit, banana, kiwi.
Okay, so write in the comments what you think the answer is and tell us all how you worked it out. Okay, we learned a ton today, but we are just scratching the surface. So if you want to learn more, make sure you join us for part 2. Thanks for watching, everyone. Please remember to like, subscribe, hit the notification bell, support the channel so I can continue bringing you more great content.